Good afternoon, everyone. I'm going to get started with the introduction now. Hello and welcome to Synthesizing Cyber Infrastructure Efforts of C4P and the EarthCube Community, a webinar series organized by C4P. C4P, Collaboration in Cyber Infrastructure for Paleogeosciences, is an EarthCube research coordination network supported by the National Science Foundation. I'm Leslie Shee, and I'll be the moderator today. Today we'll have two presentations, each 20 minutes with roughly 10 minutes for questions. We'll want to keep this to an hour, so I'll be fairly strict about enforcing time limits, and we'll give each speaker a 3-minute warning. If you have any questions, send them through the WebEx chat window to Research Coordination Networks, that user, and I will read them aloud after the presentation. You can send in a question at any time. All presentations and follow-up discussion will be publicly archived on the EarthCube website and at the C4P YouTube channel at youtube.com/Cyber4Paleo. Today, our first speaker is Andreas Schmittner from Oregon State University, and he's presenting an introduction to two Paleoceanographic projects, OC3, Ocean Circulation and Carbon Cycling, and IPODs, Investigating Past Ocean Dynamics. Our second speaker is Bruce Karen, EarthCube Program Office Manager, who will be giving a presentation from know-how to know what, why EarthCube is building the Open Geoscience Community Commons. So Andreas, I see you have the screen share now, and you can begin when ready.
All right, thank you very much, Leslie. I'm glad to be here and given the opportunity to share my thoughts on two paleoceanographic projects that I'm involved in and possible connections to EarthCube. First of all, let me just start to say that I am a climate modeler, so I usually work with global climate models. I'm trying to understand the climate system as a whole, so all of the components, including, and mostly focusing on the oceans. And this presentation and the two projects I'm going to introduce to you are community, kind of a grassroots effort to better understand the ocean circulation and carbon cycling in the last 20,000 years or so. And so we'll start with the OC3 project, which is a PAGES working group, and I have the website here for you. If you're interested, you can find more information there. This is a relatively recent effort that was launched in 2014, last summer, and PAGES, in case you don't know, is the past global changes. It is a paleoclimate project under the auspices of the IGPP, and it organizes meetings essentially and provides some funding for meetings. So the project really is, based on meetings, perhaps once a year or so, and you write a proposal to PAGES, and once you're a working group, they look at this proposal and hopefully fund meetings to get together and work on these issues. And the issue that OC3 works on is, as the title already says, understanding the ocean circulation during the last 20,000 years or so. So the science goals are how did the deep ocean circulation change during the last 21,000 years, so since the last glacial maximum to the modern period, the current period, and how those changes in the ocean circulation affected carbon cycling and storage of carbon in the ocean. And all that is related, of course, to the glacial interglacial changes in atmospheric CO2. Most people think that the CO, the carbon that was missing in the atmosphere during the last glacial maximum was stored somewhere in the ocean, but where exactly was it stored and how did it come out and why did it come out? Those are important unresolved questions that hopefully this project will help to better understand. Well, the tool that we are using to better understand the deep ocean is carbon isotope, and specifically the delta 13C. Now it has been shown for a long time that the foraminifera, and this, by the way, the symbol in the OC3 logo here in the upper right panel depicts a benthic foraminifera shell, and those are the proxy archives that are found in ocean sediments, and measurements of the carbon isotope in these calcium carbonate shells of those foraminifera allow us to reconstruct the delta 13C, the C13 of the water column at that time that the foram lived. So if we go down core, we can reconstruct past delta 13C of the dissolved inorganic carbon in the water column. Now this proxy has been used as a circulation proxy, but we know it is influenced by biological processes, mainly by fractionation during photosynthesis. So really, if we want to use it to learn something about the circulation and the biological pump, we need to assess and quantify the uncertainties. So this will be a big part of the project. And that involves, first of all, a core top calibration. So we want to know how well does this proxy represent the C13 that is actually measured in the water column. And then also the age model uncertainty. So, I've drawn this schematic graph down here that illustrates these two uncertainties. So the vertical bar on this measurement here illustrates the uncertainty of reconstructing past C13 of DIC values using the foraminifera. And the horizontal bar illustrates the age model uncertainty. So ideally, we want to quantify both of those as well as possible, although that quantification is not easy. It is difficult. But we think it is important to really make inferences from this proxy on past ocean circulation changes and changes of the biological pump. We'll also have some modeling and analysis, hopefully in the later part, last year probably or so of the project. But mainly it is a data synthesis project. We just had our first inaugural meeting. By the way, this was a joint meeting with the IPODs program, which I will talk about just a little bit later. We had that meeting in Bern, Switzerland. And well, the meeting was, of course, there was a lot of science talks, and that was very exciting. But we also talked about metadata standards and age models that we need for such a compilation, for such a synthesis project. And at the end of the meeting, we came up with this strategy for a path forward, how we want to proceed, which essentially are these 4 points. So first of all, we want to agree on data and metadata standards and that we think are important. And then we want to merge existing data compilations. And after that, we want to collect unpublished data. And in all of that, our goal is to move beyond previous compilations by creating a database that is easily updatable, that includes, for example, age model updates in the future would be easily possible, and that it's extendable in the future. So we Many previous synthesis projects have been very successful, but they have also been limited in once this product is has been produced. It is a static product. It does not evolve once the project is finished, and we want to hopefully, we have at least the ambition to go past that and go towards a system that may be updatable and extendable in the future. We'll see how far we get in this point, but I think this is a goal that is worthwhile attempting to, and I hope that maybe there's some help we can get from Cyberinfrastructure and from EarthCube in going there. Age model issues were a big topic at the meeting, and it has been argued that age model issues are the single most difficult obstacle in creating paleoceanographic data synthesis. And one of the issues that we talked about in breakout groups at the meeting was, for example, that it is not sufficient simply to have one depth in core metadata, but we also need to distinguish between the archival depth and the often modeled sub-bottom depth that can be different from the archival depth. As I understand, since I'm a modeler, I'm not a data person who goes out and gets these sediment cores, but from I understand, what my colleagues tell me is that the coring process often modifies the depth or compresses the core or extends the core so that it is the real sub-bottom depth is different from the archival depth. So that's why this distinction is important to make. And then one important age model issue is that, for example, for this time period that we are looking at, radiocarbon dating is very important, and there new radiocarbon calibrations come out after a couple of years. They are updated, the INTCAL calibrations, for example. And so what we would ideally want is a system that, where in the future we can hopefully, somewhat at least semi-automatically update the age models once new calibrations come online. And I think, again, here that the Cyberinfrastructure and EarthCube hopefully can help in that attempt to go towards that direction. And one proposal that has come up in the discussions of the project is to create kind of a central database or registry for ocean sediment cores that holds the age models, and that can be perhaps there can be different versions of the age models, and they can be citable and can be used to then connect to the data. And so that would be one way to solve this problem, or make it at least easier to deal with. Okay, let's move on to IPODs. IPODs is an international focus group of INQUA. INQUA is the International Quaternary Association, and the leader of IPODs is Luke Skinner. He's at Cambridge in the UK, and I also got the slides from him, so thank you for providing those slides to Luke. The goal, as you see here, is very similar to the OC3 goal. It is to better understand the ocean's deep circulation and how that has changed over the past 20-something thousand years, and also including its role in biogeochemical cycling and carbon cycle. The next meeting of the IPODs group will be in Cambridge later this year, and if you're interested, here's Luke's email address. Feel free to email him or me. I can forward your emails also. And maybe that brings up another point I forgot to mention. Also, OC3 both of these projects are open to the whole community, so anybody who wants to participate can do that, and just writing a quick email to me or Luke we'll set you on the email list, and you can participate. So some of the big questions that IPODs tries to answer are the dynamics of the deep ocean circulation in the past, what are the stability properties, and also how does it affect the carbon cycle in the ocean. And this diagram is just a schematic of the ocean circulation, some of the processes that we think are important, like different water masses, North Atlantic deep water and Arctic bottom water, mixing, and so on, forcing at the surface, buoyancy, and wind forcings. The proxies that IPODs considers are different from the ones that OC3 considers. So while they have similar goals, they use different proxies. And IPODs considers radiocarbon mainly, and other dynamical tracers such as protactinium-thorium ratios or epsilon neodymium. And this graph just kind of illustrates the glacial case study of how changes in North Atlantic that are associated with ice-rafted debris during the Heinrich Stadial 1 in the last deglaciation, which is around this time period from 15 to 18,000 years before the present, that caused changes in the ventilation age. Here, this black thick line in the top part of the graph shows the age difference between South Atlantic and the North Atlantic sediment core. Both of these cores are around 3,000 meters depth, and it shows that these changes very strongly during these events, during the Heinrich event, for example, here, and that these changes are also well correlated with other proxies like the protactinium-thorium proxy here shown in the gray line. That also indicates large changes in the deep ocean circulation in the Atlantic during that time. And at the same time, if you look at the bottom graph, you can see CO2 concentrations at the last glacial maximum. They were around 180 ppm, and then they started during this Heinrich event, started to increase, and they increased stepwise into the Holocene. And these increases are related to, this shows the ventilation age rate of change to these kind of pulses in the deep ocean ventilation. And this is from a paper by Luke Skinner in PNAS. So I'm almost at the end here. Topics that IPODs will tackle are also data compilation. So the goal is to compile all the radiocarbon data from the deep ocean, but also the other protactinium, thorium, and epsilon neodymium data, if possible. And something that we are talking about in there is also data reporting and quality screening issues. Then how do we, what are the ventilation metrics and their meanings, and how do we deal with reservoir ages? There are other topics like model compilation and intercomparisons that we also want to address, and then identify where gaps are and where new data collection should be done, and also perhaps recommendations for new model simulations. So to summarize, both OC3 and IPODs are dealing with synthesizing data from the last 20,000 years from the deep ocean in order to better understand and quantify changes in deep ocean circulation and also in the carbon cycle. And but currently the paleoceanographic data synthesis are very time-consuming, and they're very hard and difficult to do. Some of the issues I mentioned before, like the age model issue, but there are others, such as the current state of databases of paleoceanographic data. And so I hope that we can start collaborations with cyber scientists that may help us to go beyond the current situation and improve these issues for the whole paleoclimate community. And with that, I thank you for your attention, and I'll be ready to answer any questions you may have.
Thank you very much, Andreas. So again, you can type any questions into the chat to the host, Research Coordination Networks. So Andreas, we have a request if you're able to go back to the slide, maybe 3 from the end, which listed some of the goals and of that last project. That would help. It went by quickly.
Yes, I went over that rather quickly. I agree.
Okay. Thanks. So to get started here, some questions. Do you have a plan for the data compilation? Do you think it will be voluntary, or will there be dedicated data managers?
Yes, this is all voluntary so far. Right now, we don't have any specific funding for this project. In addition to the funds that we have from Pages and Inqua for the meetings. So those funds that we currently have only support the meetings. They don't support actual work. So that is currently in progress. And for example, I have submitted proposal to NSF that would, if funded, that would support that project. And other people also hopefully write proposals to get actual funding to do the work.
Okay, thanks. The next question is, one of your goals to agree on data and metadata standards or guidelines is quite a common one for many groups. Wondering if you have thought of what is the procedure that you will go through to get community feedback on these proposed guidelines or standards?
Well, right now what we've done is we've talked about this at the Bern meeting, and after that we had successive email conversations and iterations. So right now this conversation is restricted to the members of this project. So I have an email list, and the people who are on this email list, they get once in a while an email from me or from other people who are participating in the discussion. And so that's the main, that has been the main communication way we communicated. But maybe in the future this can be helped with maybe a research collaboration network in EarthCube, and I'm interested in perhaps writing a proposal to have such a research collaboration network for paleoclimate specifically.
Okay. Next question is, have you gotten in touch with interested cyber infrastructure researchers? Have you tried going through the EarthCube lists of members, or do you need any help with that, or have you already contacted people to work on these problems?
No, I have been, there has been a little bit of contact with Kerstin Lehnert and Doug Fills, but that is all so far. So I would be really interested in meeting people and getting to know people who are interested in this project or in this problem.
Okay, I don't see any more questions at this point, but thank you for your summary of these 2 projects. I think this is great. We now have something to sort of, show the rest of the community and try to get more people involved.
Thank you.